Okay, let's dive into lesson 2. And today we'll talk about um, both continuous and discrete probability distributions. We'll look at discrete probability distributions first. But before we do that, let's take a look at, I left you with this problem at the end of the last class, and hopefully everybody's had a chance to look at this and confirm. The answer for this is the probability of A given not B is in fact 2/3, 2 out of 3. If you did not get this, then do work to make sure that you understand how to get this, or if not, let me know if you're having issues. But the answer is 2/3. So let's go ahead now. We're going to first look at the first part of this lesson on discrete random variables. And as you can see, discrete is is the key term here, because this term discrete relates to these two words here below, that being countably finite or countably infinite. So, and the issue is countably, then in other words, you can assign integers to all of the outcomes that are available. An example of a countably finite random variable is the random variable that we looked at last time, where we rolled a die, and there were only six outcomes, and that's a countably finite random variable. A countably infinite random variable would be potentially, for example, the number of stars in the sky, or that's something that's countable, but that's very, very large number approaching infinity, or similarly the number of atoms in the universe, something of that nature that is actually countable but is exceptionally large, approaching infinity. But again, the key issue is this countable. Can you assign an integer to the outcomes? All right. We're going to next look at a specific case of a random variable, and it's called the Poisson random variable. And we're going to define this random variable as above. And we're going to put this in the context of customers arriving to a store. I like to think about a coffee shop in a lot of examples, but it's the number of arrivals or customers at a location before a specified time t. And again, this time t can be any number that the user is interested in. It's something that the user defines and would be given to you in a problem. So if for example, if we're at a coffee shop, we open the doors at time 0, and let's suppose this is 8 a.m. Then at some time later in that day, we want to know how many customers have arrived in this interval of time. And hopefully you can understand why that's an important number to be aware of. Again, it's random because we don't have any control, and there's no way to predict with certainty how many customers will arrive in this interval of time between 0 and t. But if you're running a business, that's an important number to know. And we call this random variable n of t, and it would be the way you pronounce that is n of t is how that's pronounced. So yeah. So anyway, let's look at a realization here. Now, again, we've defined this random variable n of t, and we've got this particular realization that we have a customer. This lady arrived this lady arrived at this point. Gentleman, he came here. This youngster came in the shop here, and then this person came at this point that came after time t. And so in this situation, hopefully that our random variable n of t, what value does this take on in this particular example? Well, in this particular example, n of t equals 3. And so we have 3 customers that have arrived before time t. So in general, in this, if we were in a different class, we would derive this distribution. But so for our situation, you're gonna just need to take this as a given, and we're going to use this random variable later in the course. But for now, what you should recognize is that the probability mass function, that's what PMF stands for, the probability mass function for this random variable, if we wanted to calculate the probability, and again, we've got 3 customers. If we wanted to know the chance that 3 customers, and let's just suppose t is 1 hour. If t is 1 hour, if we wanted to know the probability that n, number of customers that arrived within 1 hour, equals 3, we would use a formula of this form, where it's lambda times t raised to the x power, e to the negative lambda t, all of that divided by x factorial. All right, and so these are the key parameters of this function. First of all, we've got this term lambda, and this lambda is a Greek letter, and it is always the rate of arrivals expressed in terms of number of arrivals or number of customers per time, per increment of time. This is extremely important. And many of you, I will say right off the bat, many of you will make this mistake and not express lambda as a rate. So let me, I'll go over that in a few minutes again. And then we'll have where t, let me write back in here, lambda is this term. T is the time in the random experiment, is what we've been talking about previously. This is t. X is the number of arrivals, and again, that's how many customers have arrived. E is an interesting number. It's a constant. It's like pi. It's a transcendental number. And if you, in your calculator, if you entered, it's actually the base of the natural logarithm. If you entered into your calculator e raised to the first power, you would get this number with an infinite list of decimals, decimal places. Again, like pi, that number goes on and on forever. But called a transcendental number. It's a constant. And then x factorial is a value that's computed as it's the number of integers multiplied together. For example, 5 factorial, the term 5 factorial is 5 times 4 times 3, 5 times 4 times 3 times 2 times 1, which is 120. And by definition, 0 factorial equals 1. All of these functions would be the x factorial function, the exponential base function should be on your calculator, will be on your calculator. Okay, so let's look at an example and see how this works. Okay, you're given this information. The number of text messages that arrive at Joe's cell phone may be modeled as a Poisson random variable. On average, Joe receives a text once every 6 minutes. What is the probability that Joe receives exactly 5 texts in the next hour? So based on our previous slide, let me go back to this quickly. We need to identify lambda, we need to identify t, and we need to identify x out of this problem, because e and the terms e and x factorial are a constant, if you will. So first of all, we need to identify lambda. What is this term lambda? And it has to do with the rate at which Joe receives text messages. Now, he gets a text message once every 6 minutes, but that's not a rate. That's the time between. That is a time, 6 minutes between message arrivals. And so what I want to, I'm going to come back to this, but let me leave this for a second. All right, what is the next thing? What is the value of t? And in this case, that window of time, text within the next hour. So in this case, t is 1 hour. Okay, and then finally, what's the value of x? And in this case, we want to know the chance that he receives exactly 5 texts. So x is 5. All right, now let's go back and think about lambda. And the question you need to ask yourself, and you should see here that since t is in units of an hour, what you need to ask yourself is at what rate does Joe receive texts during an hour? So if he gets 1 message every 6 minutes, ask yourself, how many texts will he get in an hour? Well, if he gets 1 text every 6 minutes, that means he can get, on average, he will get 10 text messages . 10 text messages per hour. Okay, so that's the value of lambda. The value of t is 1 hour, and number of x is 5 texts. Oh, sorry. So next we want to define our Poisson random variable. And so now let's just say, let's let m of t, it's going to be, in the definition, the number, I'm going to abbreviate this, of number of text messages received. I'll abbreviate that, RECD, received, number of text messages received. And so then to translate this, we want to calculate, for question A, we want to calculate the probability that m, and we know t is 1. We want to know that if that equals, what's the probability that that equals exactly 5. And we know, based on our previous work, that this is going to be equal to lambda times t, all of that raised to the x power, times e to the negative lambda t all over x factorial. All right, and so now all we want to do is substitute in, and I'm going to do something over here. If you'll notice, lambda times t equals 10 times 1. And so lambda t equals 10. Okay, and so I'm just going to substitute lambda t of 10 into this equation. So this is going to be 10 raised to the 5th power times e to the negative 10 all over 5 factorial. And when we put this in the calculator, all right, and do the calculations, this comes out to be the following result: 0.0378. So about a 4% chance that he would get 5 texts in an hour. Right, about a 4% chance. Now, let me say something as an aside. In terms of grading, I am most interested in this process of your work. If you get this, that's a bonus. But this work of doing these definitions, defining these variables, all of this work is going to be a work. If you don't do this calculation, or if you make an error, that's going to be a very, very small deduction. Being able to get this answer correct is A+ work. But everything up to this point is certainly a work. All right. So I'm not testing you how well you operate your calculator as much as I am the process that you use. Okay. So let's go on to another example. Now we want to determine the probability that Joe receives no more than 3 texts in an hour. And what you'll know here is, first of all, we want to calculate a probability. We know that lambda has not changed, so lambda still stays at 10 texts per hour. In this case, what's t? What's the time window? We're interested is still in an hour, and so now we know that lambda times t still equals 10. Now what's our value of x? Our value of x equals 3. Right? So somewhat like before, we want to calculate the number of messages by time t of 1 hour is going to be less than or equal to 3. So think about our dice. We had event A that if we wanted to know if we rolled the dice and it was less than or equal to 3. This is the same type of situation, and this less than or equal to 3, okay, results from this phrase, no more than 3 texts. That relates to this less than or equal to sign. All right. So this is a little bit different situation. And so in order to calculate this, because all we have for the Poisson is a probability mass function, we're going to have to calculate, and this is going to take me a little time to get this written, but be patient. this is going to be the probability that I'm going to abbreviate that the probability that the messages in 1 hour equals 1. Excuse me, not 1, but 0, because we could get 0 messages, plus the probability that these messages equals 1, plus the probability that these messages the number of messages equals 2, plus the probability that the number of messages equals 3. Now again, that's a t in every case, and I've only put it here, but in every case, t is the same. T is always 1 hour for each one of these situations. And now we'll need to go back and manipulate and use our definition of lambda t to the x e to the negative lambda t over x factorial. And since x changes in each one of these, x is 0, it's 1 in this case, it's 2 in this case, and it's 3 in this case, we'll need to calculate this quantity 4 times, where lambda t equals 10. And so we know that lambda t equals 10. And so for the first term, this is going to be 10 raised to the 0 power times e to the negative 10 over 0 factorial. All right, and if you remember from your math classes, any number raised to the 0 power, this is 1. We know by definition 0 factorial equals 1. And so this term then just becomes the first term, e to the negative 10. Now I want you to, the solution is written up, but then you'll have a sum of a second term plus the sum of a third term plus the sum of a fourth term. And when you do these calculations, this is going to come out to be 0, very small number, 0.0103. So I would encourage you to go check and verify. So it's about a 1% chance that he would get fewer than 3 texts in 1 hour. Now let me ask a follow-on question. What's the probability that he would receive more than 3 texts per hour? More than 3 texts per hour. So what's the probability that Joe would receive more instead of no more than, in this case, more than 3 texts per hour? Okay, in this case, we'd want to calculate the probability that M, the number of messages received in 1 hour, is strictly greater than 3, which hopefully you would remember that means that he would receive number of texts in an hour would be greater than or equal to 4. Well, in order to calculate this, you'd have to calculate the probability that M is number of messages is equal to 4 plus then equal to 5 plus equal probability equal to 6, so on and so forth, forever and ever and ever. So that's really, really hard to do, but hopefully you can realize that this, by the complementary principle, this is equal to 1 minus the probability that the number of messages that received within 1 hour is less than or equal to 3. And we already know what this number is. We've already calculated this number is 0.0103. So in this case, the probability that Joe receives more than 3 texts is 0.9897. Right. By the complementary principle of probability. Hopefully, you can think through that and make sure that you understand how that works. Okay, let's look at a third example. What is the probability that Joe receives exactly 5 texts in 30 minutes? So, again, what's lambda? Has lambda changed? And the answer is no. Lambda is 10. What's t? Well, that depends, because lambda is 10 texts per hour. So what's t? Is t 30 minutes? Well, t must be expressed in the same dimensions as your lambda is expressed. So in this case, t is not 30 minutes. T is exactly 1/2 hour, which is the same. And what's x? And hopefully you can realize at this point x is equal to 5. Now I want to say something here. If you'll notice, lambda t in this case is what? It's 10 times 1/2, and that lambda t equals 5. And what I want to try to convince yourself is, let's think about this. If lambda and t, if it were 30 minutes, if we wanted to use 30 minutes, then lambda would need to be expressed in terms of number of messages per minute. And in this case, we would get, in a sense, 1 message per 6 minutes, or 1/6 message per minute. I want you to think about that and convince yourself that that's correct. So in terms, the rate is 1/6 of a message per minute. And in this case, lambda t is, hopefully you're seeing this before I'm right, is 30 times 1/6, which equals 5. And of course, in either case, this lambda t, this is 5. The key thing being that if lambda is, if the time is expressed in minutes, or what, seconds or nanoseconds or hours or days, the rate has to be expressed in the same units of time, minutes. In this case, it's hours. In this side it's hours. On this side, it's expressed in minutes. but in either situation, the lambda times t ends up being the same, which drives your solution. So now let's look at the solution. We want to calculate the probability that the number of messages that is received in, I'm going to use hours, 1t is 1/2 an hour, equals exactly 5. And using our formula, this is going to be, again, lambda t raised to the x power times e to the minus lambda t. All of that over x factorial. And now we're going to substitute in what's lambda times t. We know that's 5. And we're raising that now to x is also 5. We're going to multiply that by e to the -5. That's a negative here, -5 over 5 factorial. And this is x factorial. And again, once you do the calculator work, you'll find out this is going to be 0.175. So almost 18% chance that Joe receives exactly 5 texts in 30 minutes. And this is the next sheet is a summary of all that work that we did, just written a little bit easier, and so you can go back and refer to it. Perhaps print it out and print out this slide that'll be on D2L, and just look and study that those solutions. All right, lastly, the process that we used, and this is a process we'll see in certain forms over again. Identify the probability distribution. Then we define the random variable. In this case, that was the number of messages, the m of t, if you will. Identify the parameters, which is lambda, t, and x. Express the problem in terms of a probability statement. Transform that probability statement into the random variables PDF or CDF, the density function or distribution function, which we'll talk about. Substitute the values into that formula, calculate the value, and then answer the question given that solution. So that's the process that we'll follow over and over again. So that completes the first part of today's lesson. Next lesson will be a continuous random variable.